This is based on this paper and from this yes. I will talk about some steps called entanglement purification in QFT. First, I'd like to explain the entanglement in quantum field theory. We know that some entanglement state, we know that is fully defined rapid and very simple example is quantum systems. This is separated space, and it is product state, the entanglement state, or for example, the field state. State in QFT is actually the entanglement means that entanglement between this is some time slice, and this entanglement between A and B. A is some subregions, and B is complementary part. The entanglement in the quantum field series actually can be close to something like the space-like relations between A and B and one issue. We all the vacuum is some highly entanglement state. And we also have some non-entanglement state, for example, the boundary state in the CFTs. Why we say the vacuum is highly entanglement? Because we can use some measures to reflect the entanglement in quantum field series. The most studied one is the entanglement entropy. I think most of you may be heard of the holographic entanglement entropy is related to ADS-CFT, and this is defined by, this is the state for the whole space-time, and we choose the complementary part of A, and then we get some reduced tensor matrix. Even though the state is pure, this reduced tensor matrix is mixed. So this is the Bonoema entropy is not one even this row is pure. I say that the vacuum is highly entangled because in vacuum state in quantum field theory actually satisfies the error law of the entanglement entropy, and it diverges with the UV cutoff. We can also generalize the entanglement entropy to something called ring entropy with some parameter n, and this generation can be used to use the replay trick to detect the entanglement entropy. You can take the n to 1 limit, and you get the entanglement entropy from the ring entropy. Today, the main topic is the something called entanglement purifications. This is the plan of this talk. And first, I'd like to explain something called ring-state theorems in the algebra quantum series, and entanglement is relation with entanglement. And then about the definition of the EOP, and also the ring-state theorems can be used to relate to these quantities, and also some constraints calculation of EOP. To catch the idea underlying the ring-state theorems, I would like to use a very simple example to show what is this theorem says. Let's consider Alice and Bob. Consider two cases. The first case is that if they share the product state, for example, this kind of state, and Alice or Bob, they can construct the whole Hilbert space by local operation. Local operation means that Alice can only do something with operations in his own Hilbert space suboperators, and you can see you can get something with 1D by local operation of Alice. But in the case that if they share an entanglement state, actually we can do this. For example, if Alice make a projection, then he gets some state of this kind. And Alice can also do something, for example, use the zero node, control node gate on this state, and you can get change this state to this kind of state. Then you can make some projections. You can get all the pieces of the two quantum systems. This is definition of steering good. This means that with some control probit, if A is 1, then it changes the Alice's probit of 0 to 1, and also 1 to 0. if it is 0, then it doesn't change this the probability of values. So the Pepe resistance theorem actually says that Bob and Alice can contract their table space by performing local operations if they share a entanglement state. So the resistance theorem actually is very close to closely linked to the entanglement. To state the resistance theorems in the algebra quantum series, and this is a framework of the algebra from field series. His starting point is that for any open regions, subregions, you can define some algebras associated with these regions, something called C-star algebra. For example, I can define this kind of operator. This is some smiling fractions, and this integral is firmly in the region O. And this is a local operator, and also satisfy some macro causality relation if it doesn't like. And we can also construct the Hilbert space by working on this is the algebra for the entire spacetime. We work on the vacuum. We get the whole Hilbert spacetime, and also some satisfy the hyperduality. This means that the commutation set of this local algebra is equal to the algebra associated with the complementary part of this subregion O. The resistance theorems in the QFTs, it means that we can define the concept in the cyclical state. This cyclic state with respect to the whole Hilbert space H. It means that if this site extends in this whole Hilbert space, then we mean that this state is a cyclical state. For example, the vacuum state is cyclic state for the whole Hilbert space time, because it is just the definition of the Hilbert space. But the range systems actually see a very strong condition that it means that for any bounded region O, the vacuum state is cyclic for the local regions. And this just means that if we consider this lecture room as a quantum field series, I can build any state and only some local operations nearby myself. This is what this theorem means. And here we will discuss the vacuum state, but it can also generalize to some excited state. In this paper, some review of these topics. Okay, this is the something range systems. I want to discuss the entanglement purifications. Let's first the definition. Definition is that for given state we have two subsystems A and B, and this may be correct or disconnect something. And choose A and then you can define the reduced S matrix for this state, and this is usually mixed. For vacuum, it is actually mixed. This is mixed state, so we can always find the pure state by introducing the sum in A2 and B2, and such that it satisfies that when we choose these two radials, that we can get the same reduced S matrix of the vacuum. This is very trivial because that if it is vacuum, actually if we take this A2 and B2 to be the complementary of A and B, and this actually is the vacuum actually is a purification of this ZOAP. The entanglement purification is defined. I consider the Neumann entropy or entanglement entropy of ZOA and A2. The ZOA A2 is defined by choose part B and B2 by this pure state, and we find we choose the minimal one of this one, and then define the entanglement purifications. The definition is very complicated, and I just want to slides to explain why we would like to be interested in these quantities. It can be correct some correlations between A and B, and it's something for body visual information defined by the entanglement entropy actually can also do the synthesis, and it will satisfy some inequalities involved in this entanglement purification and visual information. I think the motivation for why we're interested in these quantities is that there are some proposals by in the momentum and this paper, there's some holographic conjecture. I will not talk about holography in this paper, but I think that this holography conjecture related to a lot of concepts in ADS-FT and also in quantum field theories. For example, the summary compute entanglement and also the surface state performance, and because it relates to some unitary operations, we will show this later. And now, what's the relation with the resonance rooms and the purifications? Because we know that the resonance rooms can be only do some local operations to contract the SH side of the whole period space. So it's if we only work some local operations in the AB complementary of AB, and we can construct this side as in the period space. So the purification is should in this side, and that consider the constraint of this this condition. And the definition should constrain that this low AB is same as the original part of this low AB. So this constraint actually we can get the condition that these operations must be unitary. And here is the so here we should use the resonance rule again. And the conclusion is just I just have a brief summary. The first step was the purification. The contractual purification can be reached from unitary operations on the complementary of AB, and this side is the purification that we need. But the second step to calculate the minimal one of Rho A and etude is very it's not so easy, because we should need to calculate the entanglement entropy of this reduced test matrix for any unitary operations in the quantum field series. In quantum field series, actually we can construct infinite unitary operations, and the calculation the entanglement entropy in this state is very hard task. But let's see what we can get some general properties of this unitary operation. Let's consider the case that let's consider the system AB. Let's consider its interval in this case, and AB and its adjunct. Here we choose that B is some point to the minus infinity. It is also okay. We can choose to some interval adjust. We can use some conformal transformation to make this to make that case to this case. Here we choose that A to the B to the like this one. A to the is near the A, and here the local operation of the unitary transformation only working on these ranges and unrelated to these ranges. You can see that the reduced depth matrix of Rho AB is invariant. It's same as the vacuum case. So these operations only affect this part, and we know that the entanglement entropy of A and A2 it usually satisfies the air law. This means it can be roughly understand that the correlations there, the boundary of A2 and B2 is very large. So this unitary operation, if we have some unitary operation that can be disentangled from A2 and B2, it may be reduced the entanglement entropy of the vacuum states. So this unitary operation can be understand some disentanglement from A2 and B2. But if it is always makes the A2 and B2 smaller, larger, this operation. Let's consider extreme case. This extreme case is that if we assume that there is some local operations such that we can make the vacuum state into some state product state of B2 and the complementary of B2. This just means that this unitary operation just make this vacuum state be a product state of this part local state. This is something called holographic compaction by this paper. It proved this in the lattice model. Here we just assume that this may be true. Let's consider we can use the archive inequality and this because that the state is still pure, so SP and A2 die is equal to SP and E2 die. So we can use this in-quantity, and we see that near this state, we will find that A and A2 die is very larger than SA. But this will conflict with the in-quantity. This is the UP we just mentioned that A2 larger than A2 smaller than SA. If the disentanglement is totally disentanglement E2 from its complementary parts, then we will get a very large SA and A2. That's esteemed how much should we disentanglement? That should say the minimal SA2 corresponds to this this state. This state it satisfies these inequalities, and in the case that we consider, and we can define the subset. This is A and A2 is defined as lambda should in this region, and we can also use some strong subactivity and also in quantity. We can roughly estimate the disentanglement it should in these regions, and here we can see that near this state, the entanglement between A2 and B2 and A and A2 is still very large. And if we consider the holographic conjecture that the lambda should be 1/2, but the holographic conjecture is cannot proved. But the conclusion is that the two correlations, the correlation between A2 and B2 and A and B2 is still very large. Okay, we can also consider some derivation near this state by some unitary operation. This is unitary operation. This is some condition operator. This is the some conditionless parameters, and this is the state produce the minimal SA and A2. This case is very trivial. It's because that it makes the determinant entropy environment. Because that you make some local unitary operations, the determinant entropy for these regions will not change. And this case is non-trivial because it can be written as the product of commission operator in A2 and B2. And the condition that we can also calculate the state variance of the determinant entropy of SA and A2. And the variance can be extended by this parameter delta. And the first order can be written like this one. This K is just the modular Hamiltonians of this reduced length matrix in these states. This condition, A and A2 is minimal in this state psi m. We can get that S1 must be vanished. This is the condition that we can get. And we can further take the case that the commission operator, a special case of this one, and we can get that this condition much stronger condition because any operators can be written as the commission operator, and we can also get very strong conditions with this. This is the condition that we get. Let's understand its condition. Its condition is that this reduced modular Hamiltonians A and A2 M is can be expanded some operators in the region A and A2, and this is the operators in this in the regions B2. We can use some non-separating properties of the vacuum, and this can be also these properties is some conclusions from the recent research. It means that any local operators work on the vacuum. Here that the spec can be written as a unitary operator working on the vacuum. Any local operators working on the vacuum can be vanished. And so this part is not vanished. And we know that in this state psi, we estimate that entanglement between A2 and B2 is still very large. So this just means that the correlations is not vanished. And the only possible is that this operator is vanished for this condition. So we can get still a very strong condition. This means that module Hamiltonians of A and the student must commutative with any operator is the operator in the or A student. Maybe we can also consider the second order. Second orders actually we have no compact forms. There is dependent terms in this. We can see whether this is some constraints. Okay. I will come to the conclusion and the future. I'll summarize that we have two steps to calculate the entanglement purification in quantum field surface. The first is we can use the resistance rules to construct the pure side of purification side of this, and this is just the unitary operation working on the white field. But the second step, to find the minimal one, is very hard. Into DCFT, for example, we take this case, and in this DCFT, we need to calculate some twin-star operator. Here is some I'm sorry, some twin-star operator in this kind of state. So it's something. It's not just a four-point function. It involves dependent for each function. So here it's not possible to calculate. For example, when you have some special cases, I don't believe that we can calculate this. Maybe more at moments I see not master to calculate this. So direct application seems not possible. But maybe this is just a starting point for understanding the holographic entanglement conditions. This condition actually is very similar to something called module zero mode condition. Not same, but similar. The module zero mode condition actually can have some holographic dual of this condition. So where it's possible to have some holographic explanation of this condition, and then some better prove the conjecture of the holographic entanglement. This may be a good starting point, and this is still something need to work. Okay, thank you.
Is also okay for possible to do for next step?
Next step. Yeah, it can be defined by for mixed state. But in the quantum series, for the vacuum state, we still don't know how to calculate this kind of quantum. But its definition is okay for mixed state, and the holographic conjecture also works for the mixed state.
This lay the black hole in the front.
Yeah, yes.
Yeah.